Section 5.1 in college algebra, they want us to graph this guy. Let's first realize that he is an exponential graph. Okay? Why is it exponential? Because the variable x is up in the exponent right there. So please take your straight edge that I have provided you. Let's make a little x-axis and a y-axis on this puppy in the same location that I have provided there. And then, obviously, we could use our calculator to make a table of values. We want to try to understand exponential graphs a little bit today, so we're going to make our table of values by hand off to the side when you're done with your axes. Just to understand them a little bit better, let's pick these x values. Let's start up here at -3 and just keep working our way, getting a little bigger each time. All the way up to 4 is what I went, just to kind of see what exponential graphs are all about again. And where I really like to start at is right here. It's not like a vertex or anything, but this is a critical place. Let's put 0 in for x. If I put 0 in for x, it says 2 to the 0th power. It's just a little memorized trick. Anything raised to the 0th power turns out to be 1. Right? So y would turn out to be 1 in that situation. If I put 1 in, I'd get 2 to the 1st power, which is 2. If I put 2 in, I'd get 2 to the 2nd power, which is 4. Putting 3 in, 2 to the 3rd power is how much? 8. 2 to the 4th power. Maybe you can see the pattern so far. What has happened? Doubled every time, right? Times 2, times 2, times 2, times 2. Why times 2 every time? What was the base in this situation? 2. Cool. Then bringing our knowledge back to negative exponents. It's been a while. If I put -1 in, I get y equals 2 to the -1st power. There was a little bit mentioned this year in a video about negative exponents. Negative exponents mean reciprocate the base. So if the base is 2, what is the reciprocal of 2, please? 1/2, and then that would be raised to whatever that number is positively, right? So it's really 1/2 to the 1st power, which is 1/2. If I put a -2 in there, again, I'd get a negative exponent. I need to reciprocate the base, so you really have 1/2, but now it's to the positive 2nd power. So you got to take 1/2 and square it. 1 squared is 1, 2 squared is 4, so what's 1/2 squared? 1/4. Cool. And then maybe that can trigger our memory of what negative exponents is all about. What would be 2 to the -3rd? It's really 1/2 to the 3rd power, which is how much? 1 what? 1/8. Y'all cool with that? And then et cetera, et cetera, et cetera. What if I went to -4? We're just going to talk about it out loud. What would y turn out to be if I had -4 for an x value? 1/16, then 1/32nd, then 1/64, then 1/128. And then it just keeps getting smaller and smaller and smaller and smaller and smaller and smaller and smaller. Will it ever reach 0? You keep taking stuff times 1/2, will it ever reach 0? Never reach 0. So let's kind of plot these. Let's make scales of 1, 2, 3, 4, 5, 6. I like to put the negatives also. It's just how I roll. And then I'm going to go by 1s on this guy also. I'm just not going to list every one. So skip a space, 2, skip a space, 4, etc. Still counting by 1s, just not every one. You okay with that? Let's plot those points. I start with that 0, 1. This is a critical point in an exponential graph. The point 0, 1 is special. Then 1, 2. Buckle your shoe. 2, 4, 3, 8, and then when I get to 4, 16, I can't even fit it on there. Then those negatives, -1, 1/2, so you got to do a little bit of rough guesstimating. -2, 1/4, -3, 1/8. Isn't that thing getting closer and closer and closer to the x-axis right there? Will it ever touch it, though? Nope. There's an asymptote there, so when you connect the dots, do your best to not touch that axis, x-axis, and then that guy will just shoot through the roof. This is your typical parent exponential function, exponential growth function. Why is it exponential growth? It's all about that base. Yep, Megan Trainor's still right. It's all about that base. If the base is bigger than 1, then that will be exponential growth. Again, if the base is bigger than 1, it'll be exponential growth. If the base is between 0 and 1, it'll be an exponential decay, which an exponential decay graph looks like this instead. It goes down from left to right. Starts really, really high, goes low, but this is exponential growth, starts low, goes high. Goes through 0, 1 each time. There is a horizontal asymptote right here. Let's sketch that guy in as a dashed line, or you can use a straight edge, I guess. Horizontal asymptote at y equals 0. Because y will never turn out to be 0. That's what we were discussing with this table of values. It's like that thing will never, ever, ever get to be 0, so that's called an asymptote. It is a horizontal asymptote at y equals 0. So you need to understand the basic sketch of this parent function before we can do the next few problems. We're okay with it so far? Next guy. Sketch the graphs of these transformations of the exponential functions. They want us to basically do the purple note card on it. We're going to do that without all the writing and all that stuff. We're just going to do it mentally, okay? And then write down the things that happen. Number 1, did it reflect over the x-axis? You look at this part right here and see if that's negative. Is it negative? Yes or no? There was no reflection over the x-axis. Number 2, is there a translation? In this case, yes. The translation, this is the stuff dealing with x, right? So my question to you is, if that says x minus 4, do you feel that it moved 4 units right or 4 units left? It's always the opposite of that guy again, right? So this translated 4 units right. Cool. Did it go up or down at all? Did they add anything to it over on this side over here, like a +3 or anything like that? No dice, so it did not go up or down. This thing translated 4 units right, and that's it. Cool. Dilation, we don't worry about that until another problem. I'll show you that. This is not a dilation thing. That's your base, right? This is going to be exponential growth. Why is it exponential growth? That base is bigger than 1. It could be a 2, it could be a 3, it could be a 1.05. Anything that's bigger than 1, exponential growth. Cool? So then it says, it doesn't really say, but here's what we need to do. We need to move the critical point. There is one critical point on an exponential graph. That's 0, 1. So we need to realize if we start with 0, 1, please write this down, 0, 1 will now move to, since it got translated 4 units right, and that is about x, take this x value and add 4 to it. Where would that move to? 4. Nothing happened to up or down, correct? So take 0 and add 1 to it. Don't you still have a 1 there, right? The point 0, 1 has now moved 4 units right to be at 4, 1. Cool? Where's my horizontal asymptote at? It started at y equals 0, correct? Did this graph move up or down at all? Did anything move up or down at all? So nothing moved up or down. Shouldn't my horizontal asymptote still be in the same place then? It starts at y equals 0. Where will it be at now? At y equals 0. So start with that asymptote first. Make yourself an axis that your paper doesn't have it. You need to make a sketch of this. It's got a horizontal asymptote at y equals 0. And then the point 0, 1 has moved to 4, 1. So just roughly guesstimate where 4, 1's at and put it. There's 4, 1. And then your exponential graph always looks the same. When it's growth, it starts really low. It goes through that particular point and then shoots through the roof. That's a rough sketch of where the graph y equals 3x. Here's the parent, right? The base is 3 both times. This guy has just moved 4 units right from that guy. Okay, let's try that again. Number 1, did it get reflected over the x-axis? This is in kind of backwards order. It's really, this is the same thing. Like, see how they have this 2 plus? You know, same thing as putting the +2 at the end. Did this guy get reflected over the x-axis? No. Was there a translation? You bet. Translation, Where did we move, left or right? 4 units right. Did we move up or down at all? 2 units up. Cool. This is exponential growth because the base is bigger than 1. I need to see where the point 0, 1 moves. 0, 1 moves to. Then take these two numbers in your translation and add them to 0, 1. 4 plus 0 would be at 4, right? 2 plus 1 would move yourself to at 3, if my pen would write that. The point 0, 1, if you move it 4 units right and 2 units up, becomes 4, 3. Cool? Where's my horizontal asymptote at? He normally starts at y equals 0. Did I shift this graph up or down at all? It went 2 units up. Well, that asymptote comes with it, right? So where would it be at then? Y equals 2. Rough sketch of him. Horizontal asymptote first. At y equals 2, put HA colon y equals 2. Then plot that critical point. It started at 0, 1. He is now at 4, 3. So that's going to be somewhere about here. 4, 3. It was exponential growth, so it starts low, goes through that critical point, and shoots through the roof. Cool. One more. Did this guy get reflected over the x-axis? Yes or no? It's about the number in front if he's negative. Didn't happen. Translation. Nothing happened to x. There was no pluses, so there's no translation either. The point 0, 1 is still going to be there so far. But then, this number in front of the parentheses has to do with dilation. Will that be a vertical dilation or a horizontal dilation if he's in front of the parentheses? Vertical or horizontal? Vertical, stretch by a factor of 5. This guy got vertically stretched by a factor of 5. Cool? That means it'll get a little skinnier. And something weird happens, something that we're not used to. Because on all the other, like purple note card problems, we always focused our attention around 0, 0. Like the parent's vertex, the parabola's vertex as a parent is at 0, 0. All the critical points of those things up there that we've dealt with so far, the critical place is at 0, 0. Our critical place is not at 0, 0 on an exponential growth problem. It's at 0, 1. You have to take this point and multiply it by 5. That's what's going on with this. So if I take this times 5, what's 0 times 5? What's 1 times 5? This point 0, 1, because of the vertical dilation, will move to 0, 5. Right? It didn't happen on all those other ones because 0, 0, if you take it times 5, you're still at 0, 0. Right? Nothing ever moved. But since this point is different than 0, 0, you have to use that multiplication factor in there also. Where's our horizontal asymptote at? Did anything move up or down in the translation? Yes or no? So it's still in the same place. Horizontal asymptote is at y equals 0. But the point 0, 1 is now at 0, 5 because of that vertical dilation. That makes it get a little weirder looking. It starts very low, again, then it starts shooting through the roof even faster, and then it totally goes 5 times faster than when it shot through the roof. That's the weirdest part, is like, people are like, doesn't that mean that shifted 5 units up? It's like, I hear you. It's like it didn't shift 5 units up. It all got multiplied by 5 in that situation, so that's why that's there. Cool? It's a tricky thing that we're not used to. Yeah. Money time. Inflation. Yay for inflation. Suppose inflation is predicted to average 4% per year from 12 to 25 in the year 2000. This means that this means that if an item costs $10,000 in one year, it'll cost 10,000 times 1.04 the next year. 1.04 because you would take 4% and it's going to increase, so you need 104% for that to go up bigger. You cool with where the 1.04 came from? Then if you did it in a year after that, you take that result times another 1.04, which we usually call that 1.04 squared. Isn't 1.04 times 1.04, 1.04 squared? If you did it a third year in a row, you take it times 1.04 again, so that would turn out to be a 1.04 cubed. They're saying, please write a function that gives the cost of that $10,000 item t years after 2012. So again, this was 1 year after 2012. That was 1.04 to the first power. This was what it looked like 2 years after 2012, 1.04 to the second power. If it was 3 years after that, wouldn't that be 1.04 to the third power? They want t years after it. So what will I have? The amount equals 10,000 times 1.04 to the tth power. Sorry. T is how many years after 2012? Graph this growth model. So let's put that in our calculator, because that will help us calculate some other things later. So y equals, clear all the stuff out that you got, 10,000 times 1.04, raise that to the x power. They tell you in part B here what your window should be on the x-axis scale. Like, remember, t is your x values. So you know on our window that t is going to go from 0 to 13. I'm actually going to go from like -2 to 13. I like to see the actual axis in my window. And then since we're starting out at $10,000, right? Like if you had this and no money whatsoever, didn't you start with $10,000, right? So my y-axis scale, it's got to go up. Let's go up to just 20,000 and see what happens. Scale, probably go by 5,000s or something. You could have went by thousands or whatever for a scale. Let's see what that looks like. Not too shabby. Let's make a sketch of that on our little paper here. This is time in years. What's on the y-axis scale? If time's on the x-axis, what's on the y-axis scale, label-wise? Money, right? Dollar bills. This point right here, when time was 0, right? How much money did we have after 0 time in the bank? 10,000. So 0, 10,000 is a good number to put on your sketch. And then what happened to it? It's growing exponentially. Notice it doesn't like totally shoot through the roof though, like those other ones that we've been graphing, but it is an exponential growth guy, because isn't your base more than 1? It's just not very much more than 1. It's 1.04, so it will grow exponentially, but very slowly. Cool? It looks like this. It says if an item costs $10,000 in 2012, use the model predict in 2025. Cool? T is years after 2012. If we're in 2025, how many years is that after 2012? 13. I've got it right here on my calculator ready to go. Don't I want to know when x is 13, right? Don't they tell me x equals 13 basically on this problem? So hit trace 13 and it'll get you the answer. Hit the trace button, type in 13 and hit equals, and it will tell you what it turned out to be. When you have an x value and you want to know a y value and you've got it graphed, just hit trace whatever that x value was again. So trace 13 is what I hit. Then that is 16650.73 or 74 if we're dealing with money here. 4. After 13 years, inflation, right? And I think you probably know a little bit about what inflation is. That means like how much stuff costs in the economy. Doesn't things keep going up and up and up and up and up, right? So in the year 2025, if an item costs $10,000 in 2012, by the year 2025 hits, if inflation stays at this same rate, that item that cost 10 grand back in the day now costs $16,650 based on this model. Cool. Just like when I was in high school, minimum wage was $4.75. Now it's like $7.25 per hour or something like that. It's called inflation, baby. You know, things go up. Next. Read that puppy. Just means I'm old. These problems are so much simpler because they usually give you the equations. Right? Here's the equation. X stands for years after 1960, right? They want to know in 2014, so you can do a little quick calculation in your calculator. Like how many years is that? 2014 take away 1960. How much is that? 54 years. So t equals 54. That's my time value. Or I guess it'd be x equals 54. My bad. That's what they were using. I don't really want, well, since we got to graph it anyway, right, if you read down to part B, right, you can graphically determine some stuff. So we might as well graph this guy if we really want to. So clear this out. 492.4 times 1.07 to the x power. Let's slow down for a second. Can you realize that this is an exponential equation? Because where is the variable x in an exponent? Is it exponential growth or exponential decay? Growth, because the base is more than 1. Let's think about our window again. Okay, check this out. Didn't we just figure out an x value of what we're really wanting to be in the 54 range? So on your x-axis scale, where do you think you want to go to? I'm just going to go straight up to 100, baby. Because I know I'm already talking about 54 years later from 1960, right? So I'm going to 100. I'll probably go by tens. Y-axis scale, way too high. I don't need to go all the way up to 20,000 because what was my starting value? This is like your starting value right here. Isn't it about 500-ish, right? And this is going to be an exponential growth, so things are going to get bigger. Where do you want to go to if you're starting at around 500 and things will get bigger? Probably 1,000. Who knows, you know? By how much? Hundreds would be decent. Go wrap it. Woo! Did I go? Let me check my window one more time. I went by. So, let's see this. 20,000, 2,000. A little better. We'll see, you know, because they want us to trace 54, right? So maybe I need to even go bigger on my window because 54 is around here and I don't see that. Remember, we went to 100 here, so it's like, hey, I want to see that. So 2,000, I'm just going to now go straight up to like 10,000 just to see things. There we go. A little bit better. Let's trace 54. Boom. Still even off my graph, but it gave me the y value. All right, so 19,012.623. Now let's put a label on that and see what that means. That's the y value in this situation. What is the y value all about? Billions of dollars. Yeah, so you know you got a dollars, and you want to put billions after it. Now let's see if you know anything about, like, when you put a decimal involved with billions. $19,012 billion doesn't really make sense. When you get to 10 billion, you can go up to 100 billion, you can get to 999,000 billion. Once you get past that mark, don't you go up to a new mark? What's the next thing after billion? Trillion. And what you do then is you have to move that decimal 3 places, because doesn't it take those 3 places to get up to that trillion? So this is about 19.12623 trillion dollars. This is the amount that it gives us in billions, but I converted it to something a little more sensible. We don't say 19,000 billion. What was your question? Oh, I missed a zero. My bad. Sorry. Thank you. 19.012 trillion dollars. Graphically determine the year when the model will reach this much trillion, right? And that's why I just talked about that, because my graph that I have right here, it's in billions. I need this to also convert to trillions. So if I move the decimal 3 places this way to go from billions to trillions, wouldn't I have to move the decimal 3 places this way to convert that back into billions? What's 28.5 trillion in billions? 28, move the decimal 3 places. Right? With me on that? Is this number right here an X value or a Y value? That's a Y value. So I can't do trace 28,500. That's for X's. When I want to know when Y is something, you go back to your calculator and you type that in as a second equation. When Y is 28,500. Does my window even go that high? No. My window goes up to 10,000. So since that's 28,000, let's make it go to 30,000. Graph them both. The first one was still our original exponential growther. The second one is when it's at that $28.5 trillion. You want to know where that's at, so that's where they intersect. So second, calculate, intersect, boom, boom, boom. X is about 59.98 years. So that's basically 60 years later, right? When did we start again, though? We started in 1960, so you got to take 1960 plus basically 60 and figure out what year that would happen. What year? 2020, baby. In the year 2020. That's when the U.S. personal income will be about $28.5 trillion, meaning add up everybody's income in the entire U.S. That's what that model predicts. Yeah. Exponential decay, sometimes called sales decay. It pays to advertise, baby. It's frequently true that weekly sales will drop rapidly for many products in an advertising campaign. The decline is called sales decay. Here's the equation. A lot of people will go, dude, that looks like a growth situation. The base is bigger than 1. Totally true. The base is bigger than 1. Check out that exponent, though. Positive or negative? Negative exponent. Doesn't that mean you're supposed to reciprocate the base? So the base is really not 2. It's really 1/2. You with me on that? That is an exponential decay. 2 ways to tell. Number 1, if your base is between 0 and 1 and you have a positive exponent, exponential decay. 2, if the exponent is negative, it's going to be a decay, which again looks like this on a graph. Starts high, goes low, there's an asymptote at y equals 0 also. So use this guy. It says we got a campaign going on. Oh, nice, Donald Trump's campaign. This formula right here is all about the decline in sales, right, after the campaign. So sales will drop rapidly for many products after a campaign ends. So I guess it's not a political campaign, it's an advertising campaign. So cool thing, iPhone 6s, right, advertising campaign. See commercials, people are like, hey, I'm going to go buy that. I'm going to go buy that. I can get a new phone. I'm going to go buy it. They stop putting commercials on, people forget about it. It's like, oh, I didn't even think about that. You know, once they end the advertising campaign, sales drop, right, because people aren't thinking about it anymore. So this is the equation that they came up with for how much the sales will drop after they stopped advertising. What is the level of sales when the advertising campaign ends? X stands for the number of weeks after the end of the campaign. So X is the number of weeks after the campaign was over with. If they say when the campaign has just ended, doesn't that mean that X should be 0, right? It just ended, and X is the number after it ended. So when it ends, that means x is at 0. If I put 0 in for x, what does this exponent right here turn out to be? What's negative 0.5 times 0? 0. What's 2 to the 0th power? 1. What's 1 times 1,000? 1,000. The level of sales will be $1,000 because the campaign just ended. Boom! That equation now starts, right? At 0 weeks, it starts. They started with $1,000 of advertising money coming in. Now 1 week later, right, wouldn't we put 1 in for x? Because it's been 1 week since the campaign has been over with. So let's punch that in. Here's what you type in, 1,000 times 2 to the negative 0.5 times 1, which is basically negative 0.5. So let me get out of here. 1,000 times 2 to the negative 0.5. So how much money are they making 1 week later after they stop putting their commercials on the air? It's money, so how many decimal places? 2 decimal places. So $707.10 or 11 cents? 11 cents. Use a graph of the function to estimate which week the sales will be 500. So I'll graph that guy. Y equals, be careful how you type this in. Don't get too far ahead of me. 1,000 times negative, I guess it's 2, sorry, raised to the, don't you have a couple of things that it's raised to? It's raised to the negative 0.5 times x. That needs to go in parentheses when you raise it to. So you got 1,000 typed in. You put a parenthesis for your base of 2. Now the exponent has more than one thing in it. So you need to put the negative 0.5x in parentheses there. So that closes that exponent. Then you need to close it again for your actual 2 to the part. With me on that? Window, all crazed up again. X-axis scale doesn't need to be very high at all. You know, we'll just go back to 10 again. Because this is like how many weeks after the campaign. 1 week, 2 weeks, 3 weeks is what we're talking about. Where did we start at? Didn't we start at $1,000? So I'm just going to go to 1,200. Why 1,200 and not too much higher? Because is this thing getting higher or lower if it's exponential decay? It's going to get lower. So then I start at 1,200. I'll just go by it. 100 is fine. Let's see what he looks like. Pretty decent graph of that guy. They wanted to know when the sales is 500. Is that an x value or a y value, my friends? X or y? That's y, so I'll go back and do y equals 500. If it was x, I could do trace 500, but it's not. It's y, and then I will find that intersection place. Intersect, enter, enter, enter. Boom, baby. Nice and neat. When was it? 2 weeks. Came out perfect. Perfect. Cool with that? According to this model, will the sales ever fall to 0? Like mathematically, here's your graph again. Will that thing ever get to 0? Sales is your y value. Will it ever get to 0? Yes or no? Realistically, that could happen. They're talking mathematically. According to this model, will it ever happen? Yes or no? No. Why not? There's a horizontal asymptote at y equals 0. You can say HA if you want to, at y equals 0. There's a horizontal asymptote at y equals 0. Realistically, it could happen. You know, it's like, oh, the sales this week came in at 0.0000003 cents. You know, it's like that you're basically making nothing, right? But numbers-wise, it'll never happen. Yeah. Oh, E. Hello, E. This is E. Nice to meet you. We'll learn more about that in 5.5. Most common formula using E is for continuous growth. PERT. Principal is P. That equals E to the rate times time power. Continuous growth. You know about some basic banking now. You can use like grow just one time a year. It could happen 2 times a year, quarterly, which is 4 times a year, monthly, which is 12 times a year. E is continuous. So here's my PERT formula. I like to put A equals for my amount. If $10,000 is invested for 15 years at 10% compounded continuously, anytime they say continuously, that's a PERT situation. What is the future value of the investment? The big thing that we'll need before we get to the next few lessons is, was this number the amount after the interest or the principal before the interest? What was that $10,000? The amount or the principal? Principal is how much you put in the bank. Was it the amount after you've earned interest, or is it the principal? It's the principal, right? So A equals 10 G's times E to the rate as a decimal. If it's 10%, what is my rate as a decimal? 0.10, or just plain old 0.1, times time in years, which is 15. I usually punch that in first so I don't have this mess of things to type in. I figure out what 0.1 times 15 is. I hope you can do that without a calculator. What's 0.1 times 15? 1.5. Then just punch this guy in from left to right. 10,000 times E. E is above your natural log button right here, right over here. E to the, it already raises it to an exponent for you, to the 1.5. Close it up. And round that to money. So $44,816.89 equals my amount. Wouldn't it be sweet if you could get 10% interest? That is a ridiculously high interest amount. First of all, you'll never find a place that gives you continuous compounding, but it's stuff like your national debt. The national debt is compounded continuously. You see that clock? I hope you've seen the national debt clock, you know. That thing just keeps running, baby, because it's compounded continuously. And it's probably at a pretty high rate also. Cool. Next. Last one, baby. Exponential decay. Used to model this radioactive material of carbon-14. That must be a big thing in science class. We do a million carbon-14 problems. So it decays over time with the amount remaining after t years given by this. Y is the exponential decay. Negative exponent, right? If 100 grams is the original amount, boom, there's your 100. How much remains after 1,000 years? Did they give me an x value or a y value? Or should I say a t value or a y value? T. Put 1,000 in, see what you get. So 100 times e to the negative 0.000120997 times 1,000 is what you type in. Make sure you put parentheses again when you're doing that e to the. Or you multiply those two numbers together first, then repunch it back in. See if you get the right number. Should it be more or less than 100? It better be less, right? I figured this out first before I tried to punch that in. I took the nasty decimal times 1,000, which for you awesome science majors moves that decimal 3 places to the right. That's what it does when you take it times 1,000. Yep. So 88.6 what? Grams? Approximately. Use graphical methods to estimate the number of years till 10 grams of carbon-14 remains. Let's just talk about what we do. What would you do? Graph this, and then what would you do with this 10? Is that an x value or is that a y value? You'd also graph y equals 10, and you'd see where they intersect. Pretty simple. Nice.